At the center of the Milky Way lies something 4 million times the mass of our Sun, warping space and time around it. Light that comes too close, within 12 million kilometers, is trapped, unable to escape. This region, defined by the event horizon, separates the universe from what happens beyond. Known as Sagittarius A star, it is a supermassive black hole. Black holes occupy the places where the most massive stars once burned brightly, found at the centers of galaxies and on the boundaries of our understanding. They form naturally, the inevitable result of gravity, when too much matter collapses into an extremely small space. Yet while the laws of nature predict their existence, they cannot fully explain them. Gravity is a quiet but relentless force, always pulling, always attracting, and never stopping. It is even pulling you right now, trying to drag you through the floor toward the center of the Earth. But the ground pushes back, and everything stays in place because of the structure of matter itself. Matter feels solid, but it is mostly empty space. Atoms, made up of tiny nuclei surrounded by electron clouds, create the illusion of solidity. These electron clouds keep atoms from getting too close, and this repulsion is what stops you from sinking through the floor. This same force is powerful enough to stabilize dying stars, even those up to twice the mass of the Sun. However, beyond that limit, gravity takes over completely, and that is where neutron stars are formed. The surface of a neutron star is a place of unimaginable force, with gravity 100 billion times stronger than on Earth. Anything that falls onto it is instantly crushed and turned into a dense soup of nucleons. If you were to fall onto a neutron star, the atoms that make up your body would be compressed into neutrons, packed so tightly they would move at nearly the speed of light as they jostle for space. This frantic motion is enough to support a neutron star with a mass of up to 2 suns. But there is a limit. Add just a little more mass, and gravity takes over completely. The city-sized star would collapse, creating a singularity in spacetime. One cosmologist described the Big Bang singularity as a day without a yesterday. A singularity born from gravitational collapse is its opposite, a moment with no tomorrow. All that remains is a dark shadow of what once was, a black hole. Let's dive into the video to explore what happens when a star collapses into a black hole, and the mysteries that lie beyond the event horizon. For centuries, our understanding of the universe was built on the foundations laid by Isaac Newton, who viewed space and time as separate, unchanging entities. Space was a vast, static stage where the drama of the cosmos unfolded, and time was an ever-flowing river that ticked uniformly for all observers. This view, intuitive and practical for everyday experiences, stood unchallenged for over 2 centuries. But in 1905, Albert Einstein transformed our perception of reality with his groundbreaking theory of relativity, weaving space and time into a single entity, space-time. The seeds of space-time unification were planted when Einstein grappled with a puzzling feature of light. James Clerk Maxwell's equations, which describe electromagnetic waves, revealed that the speed of light in a vacuum is constant, regardless of the motion of its source or the observer. This was fundamentally at odds with the Newtonian idea of relative motion. For example, if you're running toward a sound source, the sound waves seem to reach you faster. Yet light behaves differently. It maintains its speed no matter how fast you move. Einstein resolved this paradox by rethinking the very fabric of reality. He proposed that measurements of time and space are not absolute, but depend on the observer's relative motion. To preserve the constancy of light's speed, time and space must stretch, compress, and shift. This realization became the cornerstone of his special theory of relativity. One of the most astonishing consequences of Einstein's theory is the relativity of time. Imagine a spaceship traveling at a significant fraction of the speed of light. To an outside observer, the clock on the spaceship ticks more slowly compared to their own, a phenomenon called time dilation. This is not merely a trick of perception, but a measurable reality, as confirmed by experiments like the Haffel-Keating experiment. In 1971, atomic clocks were flown around the world on commercial jets. When compared to stationary clocks on Earth, the airborne clocks recorded different times. Precisely as Einstein predicted, space, too, behaves in unexpected ways. Length contraction, another relativistic effect, means that objects moving at high speeds appear shorter along their direction of motion to an outside observer. For instance, particles traveling close to the speed of light in the Large Hadron Collider perceive the 27-kilometer ring as being only a few meters long. These effects reveal that time and space are not rigid and universal. Instead, they are intertwined and malleable, forming a four-dimensional fabric known as spacetime. To understand spacetime, we must think of events, things that happen at a specific location and time, as points within this four-dimensional continuum. For example, an astronaut stepping onto the moon is not merely at a place, the moon, but also at a moment in time. These coordinates in space and time are inseparable and collectively form spacetime. Einstein's genius lay in showing that the separation between events depends on the observer. However, he also discovered something remarkable. Despite this variability, there is one quantity all observers agree upon: the spacetime interval. This invariant combines spatial and temporal separations into a single, unchanging measure, reflecting the deep interconnectedness of space and time. Special relativity describes a universe without gravity, where spacetime is flat and unchanging. But Einstein knew this was only part of the story. His next leap came with the general theory of relativity, published in 1915. Here, he introduced the idea that spacetime is not static, but can curve and warp under the influence of mass and energy. Think of spacetime as a rubber sheet. When you place a heavy object, like a bowling ball, on the sheet, it creates a dent. Smaller objects rolling nearby will follow curved paths, not because of a mysterious force pulling them, but because the sheet itself is distorted. Similarly, massive objects, like stars and planets, bend the fabric of spacetime, guiding the paths of nearby objects. This is the essence of gravity in Einstein's framework. Not a force, but the geometry of spacetime itself. The implications of curved spacetime are profound. Light, which always travels in straight lines in flat spacetime, follows curved paths near massive objects, leading to phenomena like gravitational lensing, where the light from distant stars and galaxies is bent around intervening masses, creating stunning arcs and rings in the sky. Einstein's equations also revealed that time flows more slowly in stronger gravitational fields, a phenomenon known as gravitational time dilation. This effect has been experimentally verified by placing precise atomic clocks at different altitudes. Clocks closer to Earth's surface, where gravity is stronger, tick more slowly compared to those at higher altitudes. For everyday life, this difference is minuscule, but it becomes critical in technologies like GPS, where accounting for time dilation ensures the system's accuracy. Nowhere is the unification of space and time more dramatic than near black holes. These enigmatic objects warp spacetime so severely that not even light can escape their grasp. The event horizon, a black hole's boundary, represents a point of no return, where spacetime curvature becomes infinite. Beyond this horizon, time and space as we understand them cease to exist. For an external observer, an astronaut falling toward a black hole appears to slow down, their time stretching infinitely as they approach the event horizon. To the astronaut, however, time continues normally as they plunge into the unknown. This bizarre behavior arises from the extreme warping of spacetime, a direct consequence of Einstein's equations. Spacetime is not merely a backdrop, but an active participant in the dynamics of the universe. It governs the motion of planets, the behavior of light, and the evolution of galaxies. The ripples in spacetime, known as gravitational waves, were first predicted by Einstein and later detected by the LIGO experiment in 2015. These waves, generated by colossal events like black hole mergers, carry information about their origins, opening a new window into the universe. Einstein's unification of space and time marked a profound philosophical shift. It challenged our intuitive notions of reality, replacing them with a vision where the universe is a dynamic, interconnected whole. Time is no longer an absolute tick of a cosmic clock, and space is not a static grid. Instead, they form a fluid tapestry shaped by mass, energy, and motion. This new understanding extends to the very fabric of existence. The holographic principle, inspired by black hole physics, suggests that space-time itself may be an emergent phenomenon arising from deeper quantum mechanical principles. Such ideas push the boundaries of modern physics, hinting at a reality even stranger than Einstein imagined. In 1916, just a year after Albert Einstein introduced his general theory of relativity, Karl Schwarzschild provided the first exact solution to Einstein's equations. This groundbreaking work described the geometry of spacetime around a spherical, non-rotating star. Schwarzschild's solution went on to reveal some of the most fascinating phenomena in physics, including the concept of black holes. Although the term itself was not introduced until decades later, at its core, Einstein's general relativity reshaped our understanding of gravity. It described gravity not as a force, as Isaac Newton had proposed, but as a curvature in the fabric of spacetime, caused by the presence of mass and energy. To understand this, imagine spacetime as a flexible sheet. When you place a heavy object, like a bowling ball, on the sheet, it causes the surface to bend. Smaller objects placed nearby naturally roll toward the heavy one, not because the larger object is pulling them, but because they are following the curve of the sheet. Schwarzschild's solution mathematically formalized this bending. He showed that spacetime around a massive object is not flat, but curved. The degree of curvature depends on the object's mass. For smaller objects, like the Earth, this curvature is gentle. But for extremely massive objects, like black holes, the curvature becomes so extreme that it creates a boundary from which not even light can escape. In general relativity, the curvature of spacetime is described using a mathematical framework called the metric. The metric is essentially a tool that relates the coordinates of spacetime to the actual distances and times experienced by objects within it. In flat space, such as a tabletop, the metric is simple. It reflects the familiar Pythagoras' theorem, where the distance between 2 points is calculated based on their positions. In curved spacetime, the metric becomes more complex because it must account for the bending of space and the dilation of time caused by gravity. Schwarzschild's metric was the first to describe how this works near a spherical mass. It provided a way to calculate how distances and times are stretched or compressed due to the presence of a massive object. To visualize spacetime curvature, think about the surface of the Earth. Although the Earth is round, small areas, like a football field, appear flat to us. Mathematically, you can describe distances on these small patches using flat geometry. But as you consider larger areas, the curvature of the Earth becomes apparent. The same principle applies to spacetime. While spacetime may appear flat in small regions, its curvature is evident over larger scales or near massive objects, like stars and black holes. Schwarzschild's metric takes this idea further. It reveals that spacetime is stretched not only in space, but also in time. Near a massive object, time itself slows down relative to regions farther away. This phenomenon is called gravitational time dilation. For instance, a clock positioned near the surface of a massive star ticks more slowly than a clock far from it. Schwarzschild's solution introduced a critical concept, the Schwarzschild radius. This radius defines the size of a region around a massive object where the curvature of spacetime becomes so extreme that nothing, not even light, can escape. This boundary is known as the event horizon. For an object like the Sun, if it were compressed into a sphere with a radius of about 3 kilometers, it would become a black hole, with its event horizon defined by the Schwarzschild radius. The event horizon is not a physical surface, but a point of no return. Anything crossing this boundary is irrevocably drawn toward the singularity, a point where spacetime curvature becomes infinite. Inside this region, our understanding of physics breaks down. Schwarzschild's solution initially described the spacetime around stars, but it also laid the groundwork for understanding black holes. By stripping away the matter within the Schwarzschild radius, what remains is a pure black hole, a region of spacetime defined entirely by its geometry. The curvature in this region is so severe that it creates a singularity at the center, where the density of matter and the strength of gravity become infinite. Time and space are profoundly affected near a black hole. An outside observer watching an object fall toward the event horizon would see the object slow down as it approaches the boundary. Time for the object appears to freeze as it reaches the event horizon. For the object itself, time continues as normal, and it crosses the horizon without noticing any dramatic change. The warping of spacetime has observable consequences. One of these is gravitational lensing, where light passing near a massive object is bent, creating distorted or duplicated images of distant stars or galaxies. This effect is commonly observed around massive galaxy clusters and provides valuable insights into the distribution of matter, including dark matter in the universe. Another effect is the slowing of time near massive objects, as seen in experiments with GPS satellites orbiting Earth. These satellites experience slightly weaker gravity than we do on the ground, so their onboard clocks tick faster. Engineers must account for this time dilation to ensure accurate navigation data. While Schwarzschild's metric describes the spacetime around a spherical mass, it is essential to distinguish between local and global effects. Locally, spacetime may appear flat, and objects follow straight-line paths, called geodesics. Globally, these geodesics reveal the curvature of spacetime, bending toward massive objects. This distinction helps explain why astronauts aboard the International Space Station feel weightless. They are in free fall, following a geodesic through the curved spacetime created by Earth. Though they experience no force, their path is continuously bent toward the planet, keeping them in orbit. Einstein's general relativity is remarkable because it applies universally, from small-scale interactions near planets to the vast cosmic distances between galaxies. Schwarzschild's solution is just one of many metrics that describe specific scenarios, but it set the stage for understanding more complex phenomena, including rotating black holes, known as Kerr black holes, and charged black holes, known as Reisner-Nordstrom black holes. General relativity also predicts phenomena like gravitational waves, ripples in spacetime caused by accelerating masses. These waves were first directly observed in 2015 by the LIGO experiment, confirming yet another of Einstein's predictions. One of the most counterintuitive aspects of general relativity is the interplay between time and space. Near a black hole, both are stretched to their limits. For someone falling into a black hole, time appears normal from their perspective, but to a distant observer, their motion slows to a standstill. This apparent contradiction arises because time and space are not fixed, but are part of the same dynamic fabric, influenced by gravity. The concept of geodesics helps clarify this. Objects move along the shortest paths in spacetime. But in curved spacetime, these paths are not straight. A light beam near a massive object bends because its geodesic is curved, not because it is acted upon by a force. The understanding of curved spacetime is not just theoretical. It has practical applications in technologies like GPS, which rely on precise timing and positioning. By accounting for the effects of general relativity, scientists and engineers ensure these systems function accurately. Furthermore, studying the warping of spacetime offers insights into the universe's history and structure. The cosmic microwave background, for example, shows how the distribution of matter has shaped spacetime over billions of years. At the heart of every black hole is the event horizon, an invisible boundary marking the threshold where escape becomes impossible. For a Schwarzschild black hole, which is non-rotating and spherically symmetric, the event horizon is defined by the Schwarzschild radius. This radius is directly proportional to the black hole's mass. For instance, a black hole with the mass of the Sun would have a Schwarzschild radius of just 3 kilometers. Crossing the event horizon is significant. Outside observers see objects approaching the horizon slow down, and their light redshift until they fade from view. For the falling object itself, however, nothing unusual is felt upon crossing. This peculiar behavior stems from the extreme warping of spacetime near the event horizon, a phenomenon predicted by Einstein's general theory of relativity. Black holes are not merely dense objects, they are distortions in the fabric of spacetime. As you approach a black hole, spacetime stretches and curves under the influence of gravity. Near the event horizon, the warping becomes so extreme that time slows relative to distant observers. This is gravitational time dilation, a concept proven in experiments with clocks at different altitudes on Earth. Inside the event horizon, spacetime's nature changes dramatically. Space and time effectively switch roles. The inward pull of gravity becomes as inevitable as the forward passage of time. Falling toward the singularity at the black hole's center becomes unavoidable, because it is embedded in the flow of time itself. Let us consider astronauts exploring a supermassive black hole. Their paths can be mapped on a Penrose diagram, a tool that illustrates the geometry of spacetime. Imagine 5 astronauts setting out from near the event horizon. Each of them follows a unique trajectory influenced by their actions and the immense gravity of the black hole. One astronaut, Blue, drifts freely towards the black hole's singularity. As he crosses the horizon, he notices nothing peculiar. From his perspective, the laws of physics appear unchanged, yet his fate is sealed. Within a day, as measured by his watch, he will reach the singularity, a point of infinite density, where spacetime itself ceases to exist. Another astronaut, Green, attempts to fight gravity by igniting her rocket engines after crossing the horizon. Her efforts to escape accelerate her journey toward the singularity, shortening her remaining time to less than Blue's. Magenta, on the other hand, chooses to embrace her fate but adjusts her course to accelerate toward the singularity. Her trajectory allows her to experience slightly more time than Green. Meanwhile, Red and Orange, who begin further from the event horizon, either escape the black hole entirely or linger near its edge. For observers far from the black hole, the behavior of objects nearing the event horizon appears bizarre. As a spacecraft approaches the horizon, its clock seems to slow down compared to a clock at a safe distance. This is another manifestation of gravitational time dilation. To a distant observer, it would seem as though the spacecraft never actually crosses the horizon, instead appearing frozen in time. Light emitted from the spacecraft is stretched to longer wavelengths as it climbs out of the black hole's gravity well. This phenomenon, called gravitational redshift, eventually makes the light invisible to the naked eye. Once inside the event horizon, all paths lead to the singularity. This inevitability is a direct result of how spacetime is structured within the black hole. Unlike outside, where you can choose to move in various directions, inside the event horizon, moving forward in time means moving toward the singularity. This reversal of roles between space and time is one of the most fascinating and counterintuitive aspects of black holes. It challenges our perception of movement and the nature of time itself. Anything falling into a black hole undergoes spaghettification, a term used to describe the extreme stretching caused by tidal forces. Near the singularity, the difference in gravitational pull between the head and feet of an object becomes so great that it is stretched into a thin, elongated shape. This happens because gravity is significantly stronger closer to the black hole's center. For a supermassive black hole, the tidal forces near the event horizon are relatively mild due to its large size. A person falling into such a black hole might not experience immediate spaghettification. However, for smaller black holes, the tidal forces near the event horizon are so intense that spaghettification occurs before crossing it. Direct observation of black holes is impossible, since no light escapes them. However, astronomers infer their presence through indirect evidence. The Event Horizon Telescope, a global network of radio telescopes, captured the first image of a black hole in 2019. This image showed the shadow of the black hole, surrounded by a glowing ring of hot gas and dust. Other evidence comes from observing stars orbiting invisible objects, such as Sagittarius A, the supermassive black hole at the center of the Milky Way. These stars move at incredible speeds, indicating the presence of a massive, compact object. Black holes serve as natural laboratories for studying extreme physics. They allow us to test the limits of general relativity and explore phenomena like gravitational waves, which are ripples in spacetime caused by the motion of massive objects. In 2015, the LIGO experiment detected gravitational waves from the merger of two black holes, confirming yet another prediction of Einstein's theory. Black holes, often associated with immense gravity and destruction, are just one part of the story. On the other side of the spectrum, there are concepts like white holes and wormholes, which, although theoretical, open doors to fascinating possibilities in spacetime geometry. These ideas extend our understanding of how spacetime could behave under extreme conditions. White holes are often described as the reverse of black holes. While black holes trap everything within their event horizons, white holes expel everything and allow nothing to enter. Theoretical models suggest that white holes could exist as solutions to Einstein's field equations of general relativity, just like black holes. Imagine a region of spacetime where all matter and energy are ejected outwards, forming an area that no particle can re-enter. This concept, though mathematically valid, has never been observed in nature. The white hole's existence would represent a temporal reflection of a black hole, appearing in the past rather than the future. Penrose diagrams help us visualize spacetime and its infinite aspects. A Penrose diagram for a maximally extended Schwarzschild black hole includes regions not only for the black hole itself, but also for its counterpart, a white hole. These diagrams compress infinite distances and times into a finite representation, making it easier to study the connections between different regions of spacetime. In such a diagram, the white hole corresponds to a singularity in the past. Particles or light rays emerging from this singularity travel outward, crossing a horizon that separates the white hole from other regions of spacetime. Observers in these regions may see the effects of particles emitted by the white hole, but cannot interact with it directly. Wormholes are theoretical structures that connect two separate regions of spacetime. Sometimes referred to as Einstein-Rosen bridges, wormholes were first proposed as solutions to Einstein's equations. They consist of two mouths connected by a throat, which could allow travel between distant points in the universe, or even different universes. The simplest type of wormhole is a Schwarzschild wormhole, which appears in the maximally extended Schwarzschild solution. However, this type of wormhole is non-traversable because it collapses too quickly for anything to pass through. Traversable wormholes, often popularized in science fiction, require exotic matter with negative energy density to remain open. The maximally extended Schwarzschild spacetime presents a fascinating model of the universe, incorporating both a black hole and its theoretical counterpart, a white hole. This conceptual framework, derived from Einstein's general theory of relativity, describes a universe divided into four distinct regions, each connected in ways that challenge our understanding of space and time. The first region is the outer universe, where observers reside. This is the familiar realm, far from the extreme gravitational effects of the black hole, a region governed by the predictable behavior of spacetime. The second region lies within the black hole itself, an interior domain that leads inevitably to a singularity in the future. Here, the curvature of spacetime becomes infinite, and the laws of physics as we understand them cease to apply. The model also includes a third region, another universe entirely disconnected from our own. This separate realm is accessible only through the theoretical connections within the maximally extended Schwarzschild spacetime. Finally, the fourth region is the interior of a white hole, a hypothetical entity that represents the reverse of a black hole. Unlike a black hole, which captures everything within its event horizon, a white hole expels matter and energy, with a singularity in its past rather than its future. The connection between these regions occurs through a hypothetical wormhole. This wormhole theoretically allows an observer to traverse from the black hole in one universe to the white hole in the other universe. The journey, however, remains entirely speculative. The wormhole is unstable, collapsing before any information or matter could feasibly pass through it. This instability ensures that such a passage is not physically realizable under our current understanding of physics. Despite its limitations, the maximally extended Schwarzschild spacetime provides profound insights into the potential complexity of the universe. It demonstrates how black holes, white holes, and separate universes might coexist within a single framework, pushing the boundaries of theoretical physics and inspiring further exploration into the mysteries of spacetime. Inside a wormhole, spacetime behaves in unusual ways. For an object traveling through the wormhole, time and space coordinates may appear to flip roles, similar to what happens inside a black hole. The geometry of the wormhole changes dynamically, influenced by the exotic matter needed to stabilize it. Mathematically, the Schwarzschild metric, which describes a black hole's spacetime, can be extended to include a wormhole structure. This extension shows how spacetime can curve in ways that allow connections between seemingly distant or disconnected regions. Detecting wormholes or white holes is an enormous challenge. Black holes, though invisible, reveal their presence through their gravitational influence on nearby stars and gas. White holes, by contrast, would emit energy, but not attract matter, making them even harder to identify. Wormholes present additional difficulties. Their stability requires exotic matter, which itself has not been conclusively observed. Moreover, the rapid collapse of non-traversable wormholes means that even if they form, they would vanish before we could detect them. Some theories suggest that wormholes could exist on microscopic scales as part of the quantum foam, the fluctuating structure of spacetime at the smallest scales. If true, these wormholes might play a role in the fundamental nature of spacetime, and could even connect different parts of the universe in subtle ways. Microscopic wormholes are thought to arise naturally from quantum effects and may influence phenomena like entanglement. This idea has been explored in the context of the EREPR conjecture, which posits a link between wormholes, Einstein-Rosen bridges, and quantum entanglement. In 1988, physicists Michael Morris, Kip Thorne, and Olvi Yersever proposed that advanced civilizations might construct and stabilize wormholes for interstellar travel. Such wormholes would require enormous amounts of exotic matter to keep their throats open. The construction of such a wormhole remains speculative, but the idea has fueled discussions about the possibilities of space-time manipulation. The concept of white holes ties into discussions about the arrow of time, the one-way direction in which time appears to flow. While black holes are associated with the future, where matter and energy disappear, white holes represent a past singularity, where matter and energy emerge. This symmetry raises intriguing questions about the relationship between time and space-time geometry. In 1963, mathematician Roy Kerr discovered a solution to Einstein's equations that described a spinning black hole. This model introduced a more complex geometry than the non-rotating Schwarzschild black hole. Spinning black holes, now called Kerr black holes, possess unique structures and behaviors, transforming the way we understand space-time around such objects. These black holes, characterized by their rotation, reveal phenomena that challenge conventional ideas about space, time, and energy. Kerr black holes are defined by their spin, which influences their structure. Unlike Schwarzschild black holes, they are not perfectly spherical. Their rotation causes them to bulge at the equator, forming an oblate shape. This distortion of space-time gives rise to several key regions. Kerr black holes have two event horizons instead of one. The outer event horizon marks the point beyond which nothing can escape the gravitational pull of the black hole. The inner event horizon lies closer to the singularity and separates a region of different space-time dynamics. Surrounding the outer event horizon is the ergosphere, a region where space-time is dragged along by the black hole's spin. Objects within the ergosphere cannot remain stationary relative to a distant observer. Instead, they are compelled to move in the direction of the black hole's rotation. At the core of a Kerr black hole lies the singularity. But unlike the point singularity of Schwarzschild black holes, the Kerr singularity takes the form of a ring. This ring is positioned in the equatorial plane and is surrounded by space-time distortions that defy simple descriptions. The rotation of a Kerr black hole creates a phenomenon known as frame dragging. Space-time around the black hole is twisted in the direction of its spin, an effect that grows stronger closer to the ergosphere. Frame dragging has profound implications for the behavior of matter and energy in the black hole's vicinity. In the ergosphere, the dragging of space-time is so intense that nothing can resist moving in the direction of the black hole's spin. Even light is compelled to follow this rotational flow, though particles and objects can still escape the ergosphere under the right conditions. Frame dragging facilitates processes that extract energy from the black hole. One such process is the Penrose process, which occurs within the ergosphere and allows particles to gain energy by interacting with the black hole's rotation. The Penrose process is a theoretical mechanism proposed to extract rotational energy from a Kerr black hole, exploiting the unique properties of its ergosphere. The ergosphere is a region outside the event horizon where space-time is dragged by the black hole's rotation, allowing particles to achieve negative energy states relative to distant observers. In this process, a particle enters the ergosphere and splits into two fragments. One fragment is propelled into the black hole, carrying negative energy, while the other escapes with more energy than the original particle possessed. This ingenious mechanism illustrates how energy could theoretically be siphoned from a rotating black hole's spin. The structure of space-time within a Kerr black hole undergoes remarkable changes, especially in the region between its two event horizons. These horizons, the outer and inner boundaries, delineate distinct areas with unique properties. In the space between the horizons, the behavior of space-time becomes highly unusual. Time-like paths are inexorably directed toward the inner horizon, rendering escape impossible for anything that crosses into this intermediate zone. Beyond the inner horizon lies the core region of the Kerr black hole, where the singularity resides. Unlike the point singularity of a Schwarzschild black hole, the Kerr singularity takes the form of a ring. This ring singularity introduces possibilities for paths through spacetime that are entirely absent in non-rotating black holes, hinting at fascinating and theoretical prospects for exploring the extreme environments shaped by the intense rotation and curvature of spacetime. The ring singularity of a Kerr black hole represents a departure from the idea of singularities as points. This ring structure is surrounded by a region of spacetime that exhibits exotic properties. The unique geometry of the Kerr singularity suggests that it may not necessarily terminate all paths. Instead, certain trajectories could bypass the singularity entirely, offering theoretical routes to other regions of spacetime. Theoretical extensions of the Kerr spacetime propose that the black hole may connect to other universes. These connections appear as pathways within the black hole's inner regions, leading to speculation about the existence of an infinite number of interconnected universes. If a Kerr black hole spins faster than a critical limit, its event horizons disappear, exposing the singularity. This state, called a naked singularity, defies the typical structure of black holes. Naked singularities are not shielded by an event horizon, meaning their effects could influence distant regions of spacetime. They represent a breakdown in the predictive nature of physical laws, as their behavior is no longer hidden. To address the potential chaos introduced by naked singularities, physicists have proposed the cosmic censorship conjecture, which asserts that naked singularities cannot naturally form in the universe. This conjecture remains unproven, but highlights the theoretical tension surrounding these objects. The ergosphere of a Kerr black hole is a region of spacetime where negative energy states can exist. These states arise from the interplay between the black hole's rotation and the properties of spacetime in the ergosphere. Particles within the ergosphere can acquire negative energy relative to observers at infinity. This unique property makes the ergosphere a site for energy transfer and exotic physical processes. The existence of negative energy states in the ergosphere challenges our understanding of energy conservation and highlights the intricate dynamics of rotating black holes. Detecting and studying Kerr black holes is an ongoing challenge in astrophysics. While their effects can be inferred from observations of nearby matter and light, direct detection is impossible due to the nature of black holes. Kerr black holes influence the orbits of nearby stars and gas clouds. By studying these motions, astronomers can infer the presence of a spinning black hole and estimate its mass and spin. The rotation of Kerr black holes shapes the behavior of accretion disks, structures of gas and dust spiraling into the black hole. The frame dragging effect causes these disks to align with the black hole's spin, creating observable features. The collision and merger of Kerr black holes generate gravitational waves, ripples in spacetime that propagate outward. These waves carry information about the black hole's masses and spins, providing insights into their nature. Instruments like LIGO and Virgo have detected gravitational waves from black hole mergers, confirming the existence of rotating black holes. The spin of Kerr black holes influences the waveform of the emitted gravitational waves, revealing details about their rotation and interaction. Real black holes form when massive stars collapse at the end of their life cycle. These cosmic remnants are stark demonstrations of the power of gravity. Unlike hypothetical black holes, which are defined by mathematical solutions to Einstein's equations, real black holes emerge from the death throes of stars and exhibit behaviors shaped by their environments. Understanding how these black holes form and behave requires a closer look at the processes governing stellar evolution, gravitational collapse, and the resulting spacetime geometry. Stars maintain a delicate balance between two competing forces throughout their lives: the outward pressure from nuclear fusion in their cores and the inward pull of gravity. This balance keeps a star stable for millions or even billions of years. However, When a star exhausts its nuclear fuel, it can no longer generate enough pressure to counteract gravity. For smaller stars, this collapse is halted by quantum effects, such as electron degeneracy pressure, which leads to the formation of white dwarfs. For slightly more massive stars, the collapse results in neutron stars, supported by neutron degeneracy pressure. But for stars with initial masses exceeding approximately 20 times that of the Sun, even these forces cannot prevent the inevitable: a complete gravitational collapse into a black hole. The collapse process begins with the core of the star, which rapidly contracts under its own gravity. During this stage, the outer layers of the star may explode outward in a supernova, creating a spectacular display of energy and light. Meanwhile, the core continues to collapse, becoming denser and hotter until it crosses a critical threshold known as the Schwarzschild radius. Once this happens, the core forms an event horizon, the boundary beyond which nothing, not even light, can escape. The resulting black hole is characterized by three properties: its mass, its spin, and, in rare cases, its electric charge. These parameters completely define the black hole as seen from the outside, regardless of the complex processes that led to its formation. Black holes are often described as the simplest macroscopic objects in the universe because they lack hair, a metaphorical way of saying they do not retain information about the details of the matter that formed them. Whether a black hole forms from a collapsing star, merging neutron stars, or accreting gas, the result is indistinguishable except for its mass, spin, and charge. This simplicity arises because the intense gravitational field near a black hole erases almost all information about its past, leaving behind only these fundamental characteristics. As a black hole forms, the surrounding spacetime is drastically warped. This warping is described by the Schwarzschild solution for non-rotating black holes, or the Kerr solution for rotating black holes. The Kerr solution, discovered by Roy Kerr in 1963, provides a more realistic description of most black holes, as they are expected to spin due to the angular momentum of the collapsing star. The rotation causes the black hole to bulge at its equator and introduces phenomena such as frame dragging, where spacetime itself is twisted by the black hole's spin. This effect is particularly pronounced in the region outside the event horizon, known as the ergosphere. In the ergosphere, objects are forced to move in the direction of the black hole's rotation, and particles can even gain energy by tapping into the ergosphere rotational energy of the black hole. The Penrose process is a theoretical mechanism that allows for energy extraction from a spinning black hole. In this process, a particle entering the ergosphere splits into two fragments. One fragment falls into the black hole with negative energy relative to a distant observer, effectively reducing the black hole's rotational energy. The other fragment escapes, carrying away more energy than the original particle. While the Penrose process has not been directly observed, it illustrates the unique physics enabled by the extreme spacetime curvature around black holes. Gravitational wave astronomy has revolutionized our understanding of black holes by providing direct evidence of their existence and properties. When two black holes collide and merge, they release enormous amounts of energy in the form of gravitational waves, ripples in spacetime that propagate outward at the speed of light. These waves carry information about the masses and spins of the merging black holes, allowing astronomers to reconstruct the events that led to their formation. Observations from instruments like LIGO and Virgo have confirmed that stellar mass black holes, ranging from a few to tens of solar masses, are common in the universe. Supermassive black holes, millions or billions of times the mass of the Sun, reside at the centers of most galaxies, including our own Milky Way. These giants likely formed through the accumulation of smaller black holes and gas over billions of years. Their immense gravitational influence shapes the dynamics of their host galaxies, and they are often surrounded by accretion disks, rings of gas and dust spiraling into the black hole. The friction within these disks heats the material to extreme temperatures, causing it to emit intense radiation, including X-rays. Observing this radiation has allowed astronomers to infer the presence and properties of supermassive black holes. Stellar mass black holes, on the other hand, are more elusive. They are often detected indirectly through their interactions with nearby stars or gas. In binary systems, for example, a black hole can siphon material from its companion star, forming an accretion disk that emits detectable radiation. The motions of the companion star can also reveal the mass of the unseen black hole, providing further evidence of its presence. The structure of a black hole is remarkably simple, yet profound. At the center lies the singularity, a point where the curvature of spacetime becomes infinite, and the known laws of physics break down. Surrounding the singularity is the event horizon, the surface that defines the black hole's boundary. For rotating black holes, the ergosphere lies outside the event horizon, creating a region where the effects of frame dragging dominate. This structure is not only a testament to the power of gravity, but also a challenge to our understanding of spacetime and the nature of singularities. Black holes can also influence their surroundings in dramatic ways. When a black hole accretes matter from the nearby source, it can emit powerful jets of particles along its rotational axis. These jets, accelerated to nearly the speed of light, extend far into space and can impact the formation of stars and galaxies. The mechanisms driving these jets are not yet fully understood, but are thought to involve magnetic fields and the intense energy of the accretion disk. The final fate of matter falling into a black hole remains a subject of intense study. While classical physics suggests that all matter is inevitably drawn toward the singularity, quantum effects may alter this outcome. Theoretical work on Hawking radiation, which describes how black holes can slowly lose mass and energy over time, hints at the possibility of black holes eventually evaporating. However, the timescales for such processes are extraordinarily long, far exceeding the current age of the universe. Real black holes, despite their simplicity, continue to captivate and challenge scientists. Observations from telescopes and gravitational wave detectors provide a glimpse into their behavior, while theoretical work explores the boundaries of our understanding. From stellar collapse to their immense gravitational effects, black holes remain one of the most profound manifestations of the universe's underlying laws. Black holes are not merely regions where gravity dominates so intensely that nothing can escape. They are also systems that adhere to the fundamental principles of thermodynamics. This discovery has led to profound insights into the physics of black holes and their role in the cosmos. The idea that black holes obey thermodynamic laws was first proposed in the 1970s, when physicists began noticing similarities between the behavior of black holes and the rules governing heat, energy, and entropy. The concept of black hole thermodynamics revolves around the event horizon, the boundary that separates the black hole's interior from the rest of the universe. It was found that the surface area of the event horizon plays a crucial role in understanding black hole mechanics. The area of the event horizon is proportional to the entropy of the black hole.
Entropy in thermodynamics is a measure of disorder, or the number of microscopic configurations that correspond to a macroscopic state. For black holes, this means the surface area acts as a measure of the information about the material that has fallen into them. This remarkable relationship forms the foundation of black hole thermodynamics. The laws of black hole mechanics, which parallel the laws of thermodynamics, were established as a theoretical framework to describe the behavior of these cosmic objects. The zeroth law states that the surface gravity of a black hole is constant across its event horizon. Surface gravity is analogous to temperature in a thermodynamic system. Just as temperature equalizes across a system in equilibrium, the uniform surface gravity suggests that black holes are in a kind of thermodynamic balance. The first law of black hole mechanics is analogous to the conservation of energy. This law describes how changes in a black hole's mass, rotation, and electric charge affect the area of the event horizon. For example, when a black hole consumes matter or merges with another black hole, its event horizon area increases to reflect the change in mass or angular momentum. This relationship is similar to how energy changes in a thermodynamic system
depend on the addition or removal of heat and work. The second law is one of the most intriguing aspects of black hole thermodynamics. It states that the total area of a black hole's event horizon can never decrease. This is akin to the thermodynamic principle that entropy in an isolated system always increases or remains constant. For black holes, the area law implies that black holes can only grow larger in size unless they emit radiation, a process first theorized by Stephen Hawking.
Hawking radiation, a phenomenon predicted through quantum mechanics, suggests that black holes are not completely black. Instead, they emit faint thermal radiation due to quantum effects near the event horizon. This radiation results in the loss of mass over time, leading to the gradual shrinkage of the black hole. However, the timescale for this evaporation is incredibly long for most black holes, making the process practically unobservable for large black holes in the current age of the universe. The third law of black hole mechanics parallels the thermodynamic third law, which states that it is impossible to reach absolute zero temperature. For black holes, this implies that no physical process can reduce a black hole's surface gravity to zero. In practical terms, this means that the formation of a naked singularity, a theoretical point where gravitational forces are infinitely strong without the cloak of an event horizon, is prohibited under classical physics. The relationship between black hole entropy and surface area has a mathematical elegance. Jacob Bekenstein was the first to propose that black holes should have entropy proportional to their event horizon area. Later, Stephen Hawking calculated that this entropy is given by a precise formula involving the Planck constant, the speed of light, and the gravitational constant. The resulting value is extremely large, reflecting the immense amount of information that could be encoded within a black hole. This insight transformed the understanding of black holes from simple gravitational phenomena to thermodynamic objects with rich physical properties. One of the most intriguing aspects of black hole thermodynamics is the inverse relationship between a black hole's size and its temperature. Small black holes with less mass are hotter and radiate more intensely, while larger black holes, such as supermassive black holes found at the centers of galaxies, are incredibly cold. The temperature of a stellar mass black hole is only a fraction of a degree above absolute zero, making it virtually undetectable against the background radiation of the universe. The study of black hole thermodynamics has profound implications for understanding how different physical theories interact. It combines principles from quantum mechanics, general relativity, and thermodynamics, fields that are often considered separate in physics. Black holes serve as natural laboratories for exploring these intersections, offering unique insights into the laws that govern the universe at its most extreme scales. One practical application of black hole thermodynamics is in understanding how energy behaves in systems with extreme gravitational forces. The principles derived from black hole studies have parallels in other areas of physics, such as understanding how entropy changes in high-energy particle collisions, or in the early universe during the Big Bang. These connections highlight the universal nature of thermodynamic laws and their applicability beyond traditional systems. The framework of black hole thermodynamics also provides clues about the ultimate fate of black holes. As black holes emit Hawking radiation and lose mass, their surface area decreases. But the second law is not violated because the emitted radiation contributes to the total entropy of the universe. This subtle balance between decreasing black hole area and increasing universal entropy illustrates the consistency of thermodynamic principles even in extreme conditions. Despite the success of black hole thermodynamics in explaining many properties of black holes, some challenges remain. One question involves the precise nature of the entropy associated with black holes. Entropy in classical thermodynamics is tied to the microscopic states of particles in a system, but the microscopic interpretation of black hole entropy is still not fully understood. Some theories suggest that black hole entropy could be linked to quantum states of space-time itself, but this remains an active area of research.
Another unresolved issue is the exact mechanism by which Hawking radiation allows black holes to shrink over time. While the theoretical framework is well established, the process is so slow for most black holes that observational evidence is difficult to obtain. Nonetheless, the study of Hawking radiation has spurred significant advancements in quantum field theory and has inspired experiments designed to simulate black hole-like conditions in laboratories. Black hole thermodynamics also raises questions about the role of information in physical systems. In traditional thermodynamics, the entropy of a system reflects the amount of information needed to describe its microscopic configuration.
For black holes, this raises the question of whether the information about objects that fall into a black hole is preserved or destroyed. While the thermodynamic framework suggests that the information should be encoded in the black hole's entropy, the specifics of how this occurs remain elusive. The principles of black hole thermodynamics have been tested using advanced observational techniques, including gravitational wave detectors like LIGO and Virgo, and telescopes like the Event Horizon Telescope. These tools allow scientists to study black hole mergers and observe the properties of event horizons, providing valuable data to validate theoretical predictions. Observations of gravitational waves, for example, confirm that the total horizon area of merging black holes always increases, consistent with the second law. Research into black hole thermodynamics continues to push the boundaries of physics, offering a deeper understanding of the universe's most extreme environments. By examining how black holes interact with the laws of thermodynamics, scientists have uncovered connections between seemingly disparate areas of physics, such as quantum mechanics and relativity. This ongoing exploration reveals that black holes are not just fascinating cosmic objects, but also gateways to understanding the fundamental principles that govern our universe. Hawking radiation is one of the most intriguing phenomena associated with black holes, revealing that these cosmic objects are not completely black. Instead, they emit faint radiation due to quantum mechanical effects occurring near their event horizons. This idea was first proposed in the 1970s and has become a cornerstone of modern black hole physics. The process is rooted in the peculiar properties of quantum fields in curved spacetime, which allow particle-antiparticle pairs to form momentarily, even in regions that seem empty. Space, even in a vacuum, is not truly empty. According to quantum field theory, the vacuum is a seething background of fluctuating energy. These fluctuations occasionally produce pairs of particles and antiparticles, such as an electron and a positron. Under normal circumstances, these pairs annihilate each other almost immediately, returning the borrowed energy to the vacuum. However, the intense gravitational field near a black hole's event horizon creates an unusual situation. If one of the particles in the pair crosses the event horizon while the other escapes, the annihilation cannot occur. The escaping particle becomes real and contributes to what we observe as Hawking radiation. The particle that escapes carries energy away from the black hole. By the law of conservation of energy, the black hole must lose an equivalent amount of mass. This is because, according to Einstein's mass-energy equivalence, energy and mass are interchangeable. As a result, Hawking radiation causes the black hole to gradually shrink over time. This process is incredibly slow for large black holes, as their temperatures are extremely low and the amount of radiation they emit is minuscule. The temperature of a black hole is inversely proportional to its mass. Larger black holes, such as the supermassive ones found at the centers of galaxies, have temperatures just a fraction of a degree above absolute zero. Stellar mass black holes are slightly warmer, but still cold compared to the cosmic microwave background radiation. Only hypothetical tiny black holes, with masses much smaller than that of a star, would emit detectable amounts of radiation and evaporate within a humanly conceivable time frame. The mathematics of Hawking radiation involves several key elements of physics, including general relativity, quantum mechanics,
and thermodynamics. Near the event horizon, spacetime is highly curved due to the intense gravitational field of the black hole. This curvature influences the behavior of quantum fields, creating conditions where particle-antiparticle pairs are produced more frequently. The event horizon acts as a boundary that separates the black hole's interior from the rest of the universe. For one particle of the pair to escape, it must overcome the black hole's gravitational pull, which requires energy. This energy is effectively borrowed from the black hole's mass, leading to its gradual reduction. The escaping particle's trajectory depends on its position relative to the event horizon. For the pair production process to result in radiation, one particle must have a positive energy and escape to infinity, while the other, with negative energy, falls into the black hole. The negative energy contribution reduces the total mass of the black hole. This mechanism ties the emission of Hawking radiation to the fundamental properties of the black hole, including its mass, charge, and angular momentum. Black holes with no charge or spin, known as Schwarzschild black holes, emit radiation in a simple isotropic pattern. In contrast, rotating or charged black holes have more complex emission patterns due to the additional factors influencing the particle trajectories near the event horizon. Hawking radiation also has a thermal spectrum, which means it is similar to the radiation emitted by any object with a defined temperature. The temperature of a black hole is directly related to its surface gravity and inversely proportional to its mass. This thermal nature is a direct consequence of the particle production process and reinforces the idea that black holes behave like thermodynamic systems. The radiation emitted is incredibly faint for large black holes, making it practically impossible to detect with current instruments. However, the theoretical framework describing it is robust and supported by analogies in other areas of physics. As the black hole emits radiation and loses mass, its temperature increases. This feedback mechanism means that the radiation rate accelerates as the black hole shrinks. In the final stages of evaporation, the black hole would emit increasingly intense bursts of radiation, potentially ending in a catastrophic explosion. For large black holes, this process takes far longer than the current age of the universe, so their evaporation is not a practical concern on cosmic timescales. However, for smaller hypothetical black holes, such as those that might have formed in the early universe, evaporation could occur over much shorter timescales, and their final bursts might be detectable. Hawking radiation fundamentally depends on the interplay between quantum mechanics and the curved spacetime described by general relativity. The particle-antiparticle pairs near the event horizon arise due to the uncertainty principle, a cornerstone of quantum mechanics. This principle states that certain pairs of properties, such as energy and time, cannot both be precisely known. As a result, energy fluctuations occur in the vacuum, creating the conditions for pair production. The curved spacetime near the event horizon modifies these fluctuations, making it possible for one particle to escape and become real. The discovery of Hawking radiation highlighted the surprising connection between quantum theory and general relativity. While these two fields describe very different aspects of nature, their intersection reveals the extraordinary properties of black holes. The ability of black holes to emit radiation also challenges the classical view of them as objects that can only absorb matter and energy. Instead, Hawking radiation shows that black holes interact with their surroundings in subtle but significant ways. One of the remarkable features of Hawking radiation is its universality. It is not dependent on the specific properties of the black hole, such as its size or composition, but rather on the fundamental principles of physics. This universality suggests that the process is a general feature of quantum fields in curved spacetime, applicable to any system with an event horizon. This has inspired research into analogous effects in other contexts, such as in laboratory experiments designed to simulate event horizons using fluids or other systems. The study of Hawking radiation provides important insights into the life cycle of black holes. While massive black holes grow over time by consuming matter, the emission of radiation sets a limit on their ultimate longevity. As they lose mass, their properties evolve, and their interaction with their surroundings changes. In the distant future, when the universe has expanded and cooled significantly, Hawking radiation may become the dominant process affecting black holes. At that stage, even the largest black holes would begin to evaporate, although this would occur over timescales far beyond current observational capabilities. The process of black hole evaporation is closely tied to the thermodynamic properties of black holes. The radiation emitted corresponds to a loss of energy and an increase in the entropy of the surrounding environment. This ensures that the second law of thermodynamics, which states that entropy must always increase in an isolated system, is upheld. The intricate balance between the decrease in black hole mass and the increase in universal entropy reflects the consistency of physical laws across extreme conditions. While Hawking radiation has yet to be observed directly, its theoretical foundation is supported by extensive mathematical work and analogies in other physical systems. Scientists continue to investigate ways to detect or replicate similar processes in controlled experiments, which could provide additional evidence for this remarkable phenomenon. The study of Hawking radiation remains an active and exciting area of research, offering new opportunities to explore the fundamental laws of nature. And that's the incredible story of Hawking radiation, a discovery that transformed black holes from silent cosmic giants into dynamic objects that interact with the universe. From quantum particles escaping the event horizon to the slow evaporation of black holes over eons, this phenomenon challenges how we understand space, time, and matter. It's a reminder that even in the darkest corners of the cosmos, there's so much left to uncover. If you enjoyed this journey into the physics of black holes, don't forget to like, share, and subscribe for more cosmic explorations. Until next time, stay curious.